Welcome to HVAC Sizing Tool, or HVAC Street, tutorial number 4, Duct Design. In this presentation, Bruce Clark will be covering a lot of the basics of duct design, as well as how to use this tool to make a better ducting system. So with me today is Bruce Clark of ClearResult.
Greetings.
And my name is Christopher Diamond. I work for the Northwest Energy Efficiency Alliance. This project has been funded by the Utilities of the Pacific Northwest that fund NEA, as well as support from ClearResult. The intended audience of this presentation is primarily HVAC system designers and installers that want to know about duct design using HVAC Street. In addition, this presentation can be useful for residential energy efficiency experts like raters, as well as utility program staff that are involved with programs to support high efficiency HVAC. What you're going to learn out of this workshop is to be able to design a basic duct system and the basics around that, as well as how to use the tool to do good duct design. And finally, a little bit about how to review and interpret your results. So just to be clear, this tutorial will not make you an HVAC expert. To get the most out of this training, you should be familiar with ACA Manual J and the basics of residential HVAC system design. The tool is based on ACA Manual J calculational method with some assumptions used to expedite small building system design. It is not an ACA certified tool. This report and any values, estimates, and recommendations herein are only intended to assist you in evaluating your options and should not be used in lieu of professional engineering services. Moreover, the results are as is, without any warranty or representation regarding quality, accuracy, infringement, or other usefulness. Okay, all that said, we have tested this in comparison to the ACA certified tools over hundreds of systems across the United States, and in all cases they resulted in the same system design choices. So if you've watched the other tutorials, this house is very familiar to you. It's a very simple design, has a heating load of 28,000 BTUs per hour at design, and a cooling design load of 19,500 BTUs per hour. It doesn't have any latent load because the location we used for the weather file was Kennewick, Washington. And Bruce will be covering some of the details of duct design for this very simple house.
In order to design a duct system, we have to know a few things first. First of all, we have to know the house load and the room-by-room loads. Fortunately, we've already got that covered in another webinar. After we know the room-by-room loads, what we need to know is the capacity of the fan. And you get the capacity of the fan by looking at the fan capacity table, or in some cases the fan capacity curve. As a rule of thumb, you don't want a weak fan. If you have a weak fan, chances are you will not get the performance out of the duct system that you want. After we decide what fan we're going to use in the equipment, we need to come up with a TEL. The TEL is simply, well, it's the total equivalent length, but what it is, it's the most restrictive path that an air molecule would take. And that path is entering the return grill, down the return itself, into the air handler, down the supply, and into the room. It is not the longest path, it is the most restrictive path. We'll cover more of that later. When we get that done, we have to calculate the available static pressure. Quite simply, that's the amount of static pressure left to push the air through the ducts after such devices as, return grills, supply grills, filters, and air conditioner or heat pump coils. After we have that, we can finally calculate what is known as the friction rate. This is the part that's on your ductulator that I'm sure you've seen before. Mathematically, it's expressed as the available static pressure times 100 divided by the total equivalent length. Generally, it varies from 0.06 to 0.12. When we get that, then we can begin to size each duct in our system. This is an example of a fan table or fan curve or fan capacity table. As you can see, it lists several models at once. Since we're putting a two-ton system in, we're going to use this gas furnace with a 2-ton, the 24 with a 2-ton blower in it. Notice we have 4 speeds available to us, and underneath the external static pressure that the fan has to operate against, you will see how much air it's capable of moving. So, well, what we can tell is if we get too high a static pressure in our duct system, we're not going to move enough air. Our goal is to move at least 800 CFM worth of air. So if we look at 0.5 on high speed, we can get 807. So it's going to be pretty close, but I think that we can do it. So again, what this table tells us that on high speed, this particular furnace with a 2-ton blower on it is capable of moving 807 CFM into half an inch of water column. Every fitting in a duct system exerts a certain amount of resistance to airflow. The best way to describe that is EL. EL is equivalent length. If you go up here in the upper left-hand corner, we'll see that this fitting coming off an air handler has an EL of only 10 feet. That means it's equivalent to resistance of 10 feet of straight pipe. Notice it has turning vanes. If we go down to a similar fitting without turning vanes, it has an EL of 120 feet. Hopefully the simplest thing I say today is that 50 feet of straight metal pipe has an EL of 50 feet. On the other hand, flex duct, improperly installed, say it has 15% compression, that 50 feet of flex duct can have an EL of 100 feet.
So Bruce, HVAC Street has a whole bunch of menu options for ACA Manual D fittings, and it's really confusing, honestly. There are, however, a couple of options at the top. One says good, one says medium, and one says bad. Can you talk a little bit about these different fitting options?
Absolutely. Well, I urge everybody to become familiar with fitting types. There is sort of a shortcut. And essentially, a fitting to be considered good is if the EL of that particular fitting is below 20 feet. The medium option is basically going to be between 20 and 50 feet, and the bad is over 50 feet. And we shall see that some of these fittings are really bad all by themselves. The biggest difference is it a hard left or a hard right? In this fitting right here with no turning vanes, we can look down, and depending on the length to height ratio, the EL of that one fitting can range between 160 and 260. Just look what difference a set of turning vanes make. All of a sudden, because we break up that turbulent flow into a bunch of smooth, rounded turns, we drop it all the way down to 10 feet. Here's a really bad example. We call this the headbanger in the basement. We go right hand, right hand, right hand, right hand turn. And those fittings, this one fitting to get around that beam in the basement can give you up to 400 feet of EL. But just by putting in 45-degree turns, again, no lefts, no hard rights, we can bring that EL all the way down to 20 feet.
So in our tutorial house, the entire EL, the total effective length of the entire duct system, the longest, most restrictive path, is less than 470.
Yes.
So if we put one of these headbangers in there, we would have had...
We would have doubled it.
Ouch.
Many people in the audience today have used the ductulator. But I want to emphasize that while the ductulator is very useful, and especially if used correctly, it is a great tool. However, many people use it incorrectly. I just want to state right now that duct sizing is not the ductulator alone. The simplest way to understand the friction rate is simply a way to gauge the restriction of airflow within the duct system. We urge that you keep the friction rate low. Why is that important? If you have an ECM blower, it will lower the fan energy use. It will result in reduced noise levels, and also it will result in better filtration because the air has greater residency time going through the filter. How you calculate it is the available static pressure times 100 divided by the TEL, or total equivalent length. The total equivalent length, or TEL, is not the longest length in terms of footage. It is the most restrictive path that an air molecule must follow from entering the return grill, down the return system, into the air handler, and eventually out the supply grill. This illustration on this slide shows why that is true. Example number 1 shows that, wow, this looks long, but we have an EL of 5 feet. And then we have a turning vane system here with only an EL of 10. We go through 20 feet of straight duct and then through the fitting right before the exit grill with an EL of 12 feet. Example number 2 down here is that we have a shorter path but its restriction is much greater. We have the same EL, but rather than going through turning vanes, we take a hard right-hand turn with no rounded corners, no turning vanes in it. And then we enter, probably about 20 feet of poorly installed flex duct, which doubles the footage and gives you an EL of 40 feet. And then finally, out the exit grill, which has an EL of 20 feet, probably not a very good one. And so as a result, the TEL of the system is 125 feet, not 47 feet. The first step in calculating the available static pressure is to know what the total external static pressure will be. When you look at your fan capacity tables, it will give you the static pressure generated by the fan. So we can see here is generally from the filter, on the fan side of the filter, to the exit from the fan. This is true for gas furnaces with air conditioning. If this was a heat pump system, the fan curves are designed in such a way that it's actually taken after the coil in the system. So we start with the total external static pressure, and then we subtract the pressure drops from the devices placed in the duct system. That device can be a filter, that device can be an air conditioner coil, it can be a damper, it can be a UV light. It also includes the pressure drop in the return grills and out the supply grills. There are two basic approaches to designing a duct system. Hopefully I'll convince you one is superior to the other. The first one is have a adequately sized fan, use good duct design practices, or just plain big ducts. The benefits of using this approach is you get some energy savings because the pressure in the duct system is lower, so any leaks have a lower pressure drop across the leak and less leakage will occur. Also, it'll keep the system noise quiet. The other approach is to put a really big fan into a restrictive duct design in small ducts. This can work. You risk customer complaints and you risk high energy use, especially using an ECM fan. Both approaches can result in a target friction rate of between 0.07 and 0.12, and that's inches of air pressure per 100 feet of EL. Again, good design, adequately sized fan is superior to putting a large fan and designing the ductwork poorly. The duct design process begins on the System tab. It's at the bottom of the tab, and the first question we have to ask is equipment specification. If you don't want to enter anything, that's fine. It's primarily for record-keeping purposes. There's a wide range of manufacturers. You can keep track of serial numbers. The real work begins underneath the duct design preferences. You've got your choice of the usual duct board, metal, or wire helix, also called flex. We're going to stick with flex. The maximum number of CFMs per register is critical. In no case go above 200. I personally like to use 150. Some designers go as low as 125. Maximum duct velocity, this is primarily a noise preference. Never go above 800. Some people like it a little quieter. We're going to use 700 feet. Both these pieces of information will go into the duct sizing. Underneath fan performance, this is where we need the capacity of the fans, how much air it can move, how much static pressure it can move that air against. So we're going to move 800 CFM because we have a 2-ton air conditioner. So we've looked it up and we see this system can move 800 CFM at 0.7 inches of water column. So we go ahead and we enter 0.7 for both heating and cooling. If there's other adjustments, you can go ahead and make them here. We notice that our coil that we're using in the system has a pressure drop of 0.25 inches. We're going to use a filter with a 0.10 pressure drop across it. This is really important. There's a lot of high MERV filters out there that have a pressure drop or a pressure resistance of 0.25 inches, which is the same as a coil, so be careful. This is where the 4 and 6 inches pleated filters really can make a big advantage. They can give you great filtration with a relatively small static pressure drop across it. We have to account for both the supply outlet and the return grill, and those are typically around 0.03. It tells us our total pressure drop. It takes the total pressure drop, subtracts all the adjustments that we made, and we have available static pressure of 0.29. This is the amount of pressure that you have to actually move the air down the ductwork. HVAC Street allows you to configure your duct design process to those ducts that you happen to carry in your shop. You can do this by going to the configuration tab over here and clicking on my duct sizes. Over here to the left, you can see every possible duct size that you could possibly buy. Well, most shops don't carry 3-inch, so we'll go ahead and get rid of that. And when you get rid of it, they'll never recommend that you install a 3-inch ductwork. Let's go ahead and get rid of 5-inch also, because we don't install many of those. And quite frankly, if you're carrying 6 and 8s, 7, you just don't get too much call for that anyway. Okay, so now that we've configured the ducts to the way we like it, we'll go on to the next step. Before we start the duct design process, let's revisit our tutorial house. Again, it's a simple house. It's 1,200 square feet. We have a living room, a bedroom, 1 bedroom 2, and a bathroom and a kitchen area. Our job is to get air into each one of those rooms.
Alright, so now I'm going to show you a little bit about the graphic user interface that comes with HVAC Street. When you select the Duct Design tab, it brings up this neat little graph paper representation of your design. And from here, you can see all these pieces of equipment. All these rooms out here labeled, those are all just the default supply registers that you've entered in the names of. And you can click and drag and move these items around if you want. But ultimately what we're going to do is we're going to draw lines between them to connect them through different parts. For example, if I want to add a return, I'm going to click and I'm going to drag it out onto the table. And now I'm going to connect the return air to the air handler. It puts a little circle here to have me enter the length of that ductwork. And I could enter 15 feet. I can also add other components in this thing, in which might be supply air fittings and the light. Generally you want to use good, medium, or bad. We'll just drag out a medium quality one and we'll connect lines. So next up, Bruce is going to show you a little bit more about our tutorial house, but I thought it'd be good just to go back and give you a little bit of an insight of what this graphic user interface is about.
We can now begin to design and size our duct system. When you first open the duct design page, you'll see all the rooms entered on the right hand side. We have a couple bedrooms and a big room. It's a very simple house. Also notice that there's 3 registers. Each of those big blue dots in the big room is a register. That's based on how the maximum number of CFM per register that you entered on the previous page, which was 150. So the room's already pre-populated. We just now have to, if you will, connect the dots. We can now get started on the duct design process. This process will help us determine the TEL and the size of the ductwork. The parts list on the left contains every HVAC fitting you could ever imagine. It's strongly encouraged that you use ACCA's Manual D during this process. It'll list every fitting you've ever seen or ever imagined. So to get started, we're going to put a return in. So we'll click on 0, which is returns. We'll drag a return on over. It's red, so it tells us, hey, we want some information. So we're going to only have 1 return in this house, so we're going to say 100% of the air is going to go through this 1 return. If you're putting in 2 returns, you could go 50-50 or whatever mix you so design. So go ahead and hit save. Go back to our parts. We have to connect something to our return, so we'll go down here and we'll pick on 8. We're going to put an elbow coming off the return. And rather than going through the long list of different types, we're just going to pick a medium. That's a medium equivalent length. We'll go ahead and drag that on over. It has an EL of 40. We have to connect everything. And all we do is draw a line between the two and enter how many feet those 2 things are apart. Well, the elbow is connected directly to the return, so we're just going to say 1 foot. You have to enter something. Go ahead and hit save. Then afterwards we can go ahead and switch that on back. Okay, now let's look at our air handler. We're going to go to parts again. We're going to drag another return in there. And then we're going to go to a 5, a return air fitting. We're going to pick a medium, and this is the device or the fitting that fits directly onto the air handler. So we just have to connect the dots. And again, there's no spatiality to this program. There's no scaling. You can put anything you want because you define how many feet everything happens to be. So let's go ahead and connect the two elbows. We'll say it's 30 feet. That connects to the return fitting at the air handler. That's going to be another 1-footer. And then finally we'll connect the return fitting directly to there. And we'll enter a 1. After we got everything entered, we can go ahead and push everything together for just space constraints or just however we want to organize it. Notice up here it is already calculating the TL. We currently have 153 feet of TEL. So let's go ahead and start entering the supply side. We'll go ahead, we have a supply side fitting. We're going to pick a medium 1 there too. So that's immediately coming off the air handler. We'll go ahead and just put that right here. Go ahead and connect it. We're going to have a main trunk system on this. So we're going to go ahead and we'll start with the big room. And if you're curious, why did it say there's 3 registers in the big room? It divides things up based on our previous input of the maximum number of CFM that you want coming out of each register. So what we'll do is we'll kind of start backwards. We will go, what's going to come off that register in one of the big rooms? Oh, we're going to have a supply air boot. We'll say it's a bad one that just isn't very conducive to good airflow. Wow, 80 feet right off the bat. Should probably pick another one, but we'll just see. So we'll go ahead and connect that. It's directly connected. And like all good duct designers, we're going to go back and put an elbow before we actually put the boot in there. We'll go ahead, we'll pick a medium 1 there. And we'll connect the dots again using 1 foot again. And then we're going to connect. We need to have an elbow a takeoff coming off of the supply main duct that we're going to put in there. And we are going to do that. We're going to pick number 2, and this is the branch takeoff from the main trunk line. We'll pick a medium 1 there. Okay, so now we have to connect everything. Okay, so between the supply takeoff coming off of the air handler and that takeoff, we're going to say that's all of 30 feet. So we'll go ahead and hit save. Between that takeoff and the elbow going to the boot, we'll say is another 10 feet. Let's go ahead and hit save. We now have one path created. Upstairs, we can look here and it says 416 feet. So what we're going to do now is we're going to pause for a while, and then we'll come back, and the next slide will show you the finished slideshow. For simplicity check, we took a few shortcuts. Please notice on the TEL here that the thickest line is the TEL. If one of these other duct runs was the TEL, it too would be thick. Because I already knew what fittings I was going to use on each of the individual duct runs, and this was my longest one in length, I only added the fittings to these parts. So you can see here, I just do a quick line to the other registers in the house, and we have our duct design finished. Let's go ahead and hit save. The last step in the process is to go back to the main menu, hit duct results. And when you hit duct results, you will see that you have the total TEL here, your friction rate that we're using, and again, our duct design. Please notice that each section of ductwork is size 16-inch return. That makes a lot of sense. 16-inch main supply, 10-inch going down, 8-inch, and it also shows the amount of air in CFM coming out of each register in the house. And now that concludes the duct sizing portion of this webinar.
Wow, Bruce, that was a lot of information. I'm going to try to remember three things. If you can just kind of give me a little bit of a reminder, what were the three important things?
Absolutely. The most restrictive path is the most important, and we call that the TEL, or the total equivalent length. And paradoxically, it's not always the longest path, it's the most restrictive path. The second item I want you to focus on is the friction rate. A lot of you are always using 0.10 because that's what somebody told you when they gave you the duculator a long time ago. If HVAC Street calculates it to be below 0.07, you don't have enough ESP. What that means is you don't have enough oomph to successfully get the air through the system with adequate velocity to mix the air in the room.
So HVAC Street is increasing the size of the ducts because of the lack of oomph? Is that what you're telling me?
That's a good way to do it. The less the oomph in the duct system, the bigger the ducts will be.
All right, and the opposite sort of true too.
The opposite's absolutely true. If it's higher than 0.12, you need to lower your TEL. Basically, you can put a really big fan with lots of oomph on a small duct system, and yes, you'll get adequate amounts of air, but boy, it's going to be loud, velocity will be too high, and people will complain about cold air blowing on them in the wintertime.
All right, cool.
Another thing I'd really like to emphasize, that unless you really trust your duct installer, is that HVAC Street assumes that it's almost perfectly installed flex duct. That means a good faith effort is made to pull it as tight as possible. It's about 4 to 5%. That's why if you're using flex duct, it'll always select at least one size bigger than if it's straight sheet metal. But that one size bigger, again, that assumes that it's almost perfectly installed. And unless you really trust your duct installer again, you might want to double the length of the duct, because that's what happens when you get about 15% compression. Every 10 feet of flex duct is equal to about 20 feet of sheet metal ductwork.
So if I'm looking at a 15% compression, does it look compressed?
15% sort of looks like the Loch Ness monster, and that the owner of the company might not trust their employers with duct knives.
And 4% looks like someone yanked the heck out of it.
4% is perfect. When I see 4%, people have made their best effort to pull it tight. They're using Panduit straps on the end, and it's a thing of beauty.
Cool. Congratulations, you've just finished the fourth of the tutorial series, which means you've gone through getting started, entering a building, entering a system, and now duct design. There's a couple more that are available if you want to watch those as well. And if you want to learn more about good HVAC system design and residential energy efficiency, join us at the Home Efficiency Forum each year. This year in 2019, it's going to be in Portland, and it moves around the Northwest once a year. Another great source of information is www.betterbuiltnw.com. Thanks very much.